All right, lads and ladies, welcome back to Honors Calc 1. I hope everybody had a pleasant weekend, a nice holiday yesterday, however you like to celebrate that. Today we're going to continue talking about what we were starting to talk about last Friday. Last Friday we introduced implicit differentiation, and we saw a little bit how to take derivatives of these expressions that involve both x and y. We call implicit expressions. We also saw how we can use that to get the derivative of the natural log function and inverse trig functions, functions that are in general defined to be the inverse of some other function. It's a neat trick. And it kind of sat on top of this thing called the inverse function theorem, which we're not going to go over in a lot of detail. I invited you guys to read the Wikipedia page for that. I still invite you to read that. It's a great page. If a little bit hard to understand from our perspective, just slightly over our pay grade, if you know what I mean. But today, we're going to begin looking at some of the utility of implicit differentiation. So today is the 15th. It's of course MAC2311.0H1. Today, we're going to look at some more implicit differentiation. This is section 3.5. We're going to look at log derivatives, which we've technically sort of looked at, but believe me, there's some cool shit here to play with. This is section 3.6. It's not heavily represented in your homework. I think I only put like 3 or 4 problems in there, but this is actually a really cool thing. And while we won't likely do it today, we might introduce related rates. Related rates, this is section 3.9, so we make a jump in the textbook here. And it's the last section from chapter 3. The related rates section tends to be a little bit hard, but it really depends on 2 big things. First, how comfy are you with implicit differentiation? Because all of the derivatives you take in this section are done implicitly. The other thing is kind of how comfy are you with word problems? Because a lot of these related rates things, they come from the real world. And that's one of the things that makes them so beautiful is, all of the related rate stuff is stuff that has intimate connections to physics or other bits of geometry in the real world, which can make them tricky also because you got to be kind of comfy drawing pictures and moving between 2 realms where you've got like algebra and the abstract mathematics over here, and then you've got like pictures, geometry, and the physics that's going on over here. I try to be very light on this stuff, right? My view is that this is a math class, not a physics class. So I'm not going to beat you guys to death with the little techniques from physics. If you want to do that, take physics 1. But I will be using some of them. We have to use some of them. And certainly we will be quite heavy on the math stuff, right? So I hope you guys enjoy the related rates section. I invite you to read it ahead of time. It would be very wise for you after today's lecture to read section 3.9, because I think the implicit differentiation, especially in this class, we've spent a little bit of time on it already. And I don't think you'll struggle with this. The log derivatives, this is cool, but again, I don't think you'll struggle with it. This is going to be all new to us today. If we talk about it at all. And it's going to be something that is probably a little bit challenging when we get to the meat of it, even if you've seen some of those concepts before. So let's get moving. The implicit differentiation we've done quite a bit of. So I'll just say for implicit differentiation, remember the move here is we can differentiate expressions involving both x and y by assuming that y is a function of x using the chain rule. And of course, there's really nothing special about the labels x and y. We could do this with any independent and dependent variable pair. So if you had like t and s, or anything like that, as long as you can identify the independent variable and the dependent variable, then you can apply the same sort of rules. I'll do one little exercise to kind of warm us back up. We did a little bit of this previously. Let's take a look at number 20. Well, 25 you can do in the book, find the answer in the back of the book. Let's take a look at 26. This is an even numbered question. So just to kind of remind you, I'll write this down and work through this easy problem. Then we'll look at the inverse trig stuff again quickly this time, and then we're going to move on. So find that equation again. I'm just going to write this down, and then we'll go back of the tangent line to sine of x plus y equals 2x minus 2y at the point pi comma pi. All right, here's the problem down here that we're going to solve. This is our kind of warm up. So we did plenty of implicit differentiation last week. I just want to make sure we remember how all that goes, and nice to look at a tangent line problem instead of a just find y prime problem. To find any line, you need a point and a slope. They gave us the point. So my point is definitely this point, pi comma pi. To find my slope, I need y prime, right? Y prime or dy dx, that's what gives me the slope of the tangent line. And we get this via implicit differentiation. Because this expression is not solved for y. I don't have an explicit expression. So if I want to get y primed out of what I have, I need to differentiate through this expression implicitly and then solve for y primed. So I'm going to apply the differential operator d dx to both sides of the expression above. That's all. That's going to be on the left d dx of the sine of x plus y equals on the right d dx of 2x minus 2y. On the left-hand side, I will need to use the chain rule because I've got like an outer function here and an inner function here. The right-hand side here is a straight up derivative, but you got to remember when you differentiate the 2y, how that works. So the derivative of 2x is just 2. Minus the derivative of 2y, if we were differentiating with respect to y, would just be 2. But I'm differentiating with respect to x. So d dx of 2y is 2, that's the derivative of the outer, times the derivative of the inner, which is y primed. And then on the left-hand side, the derivative of the outer here is sine, derivative that is cosine. So I'll have cosine of x plus y times the derivative of x plus y, which is 1 plus y primed. Again, this y becomes a y primed, just like this y becomes a y primed, because the derivative I'm taking is d dx. So d dx of y is dy dx is y primed. Any questions about where this line comes from? Okay, so I need to solve for y prime, right? I want to find the equation of the tangent line at the point pi comma pi. Sometimes we can get away without solving for y primed. In fact, we could get away with that here if we wanted to, but I think it's a good exercise, especially since this is our first problem coming back from the weekend. So who can tell me how I would solve for y prime in an expression like this? What would be a good first step? Yeah, so Tahara asks a really good question privately in chat. I'm sorry to expose it here, but this is an important thing. So we're differentiating implicitly with respect to the variable x. So y is d dx of y equal to y primed and not 1. Remember, the assumption that's built in when we do these things is implicit differentiation assumes that y is a function of x. I'll call it f of x. So d dx of y is really d dx of f of x, which is f primed of x, or y primed, which is different from d dy of y, which would be 1, right? So d dy of y, that is 1. If you differentiate y with respect to the variable y, you get 1. But if you differentiate y with respect to the variable x, the idea is that since y is the dependent variable and it is a function of the independent variable x, the derivative of y is not just 1, it's 1 times the derivative of the inside, which is y primed. So I hope that that helps a little bit. This is kind of the whole thing with implicit differentiation, is that when we bump into the derivative of your dependent variable, you have to kind of think about this in terms of the chain rule. So maybe I'll go back and do one more example like this just to make sure we're super duper comfy before we move on. But for the time being, let's finish what we have here. I'll ask you to trust me that the derivative of x plus y taken with respect to x really is 1 plus y prime. It's for precisely this reason, but I think maybe we need to see some more examples to remind ourselves, and that's fine. My next step would be to try and put some things together. Yeah, Katie's recommendation is not a bad one, but I think we need to be a little bit careful about what we mean by they, so, or them, which things are like terms. I would like to get y prime on its own, but y prime occurs here, and it also occurs here. All right, my goal is to solve for y prime. So to do that, I need to get all the terms that have a y prime in them on one side, and all the terms that don't have a y prime in them on the other side. So first, I'm going to take this piece here, cos of x plus y, and distribute it over this binomial. That will give me cos of x plus y times 1 plus cos of x plus y times y prime. And the right-hand side is still 2 minus 2y prime. So these are not like terms. I can't combine them. Right? This 2 is a constant. This guy has a y prime attached. But the y prime here and this stuff is a like term with the y prime here and this thing. So now this term, this is a single term and it has a y primed. This is a single term and it doesn't have a y primed. This is a single term and it has a y prime, and this is a single term and it does not have a y prime. So the stuff without y primes, the 2 and this cos of x plus y, I want to push those over to the right. And this term, cos of x plus y times y primed, and this term, 2y primed, I'm going to push those to the left. So every piece that has a y primed is going to the left. Every piece that does not have a y primed is going to the right. That will give me cos of x plus y times y prime, that is this piece right here, and then plus 2y primed, that's this piece added over, equals 2, that's this piece coming along, minus cos of x plus y. Does everybody follow the algebra there? The miracle of doing this, the trick, is once you have a y prime everywhere on this side, you can factor out the y prime and then divide over by whatever's left. So this is equivalent to cos x plus y plus 2 all times y prime equals 2 minus cos of x plus y. And now I've got a y prime factored out on the right here, nothing else, just this chunk times y primed. So to get y primed alone, I divide over by this chunk. And that will yield y prime equals 2 minus the cosine of x plus y divided by the cosine of x plus y plus 2. And then I have some fun algebra questions for y'all. First though, let's take questions up to this point. I like Tahara's early question, by the way. I will be coming back to that. I don't think you guys saw it. I think it was sent privately in chat. But don't worry, Tahara. I will come back to your question after we finish this. We'll look at that carefully. But are there any other questions? So I think Katie was asking, are the y prime pieces like terms? And the answer there is yes. That's what I did here, is I kind of put the two y prime pieces together. Like if I had 5y prime plus 2y prime, that would be 7 times y prime. Here I just had cos x plus y times y prime plus 2y prime. So that's cos x plus y plus 2 times y prime. So those can go together. Any other questions about how we got to here? Okay then. My fun algebra questions for you guys. Can I cancel the 2's? Can this and this cancel? Yeah, good. No, I cannot cancel the 2's here, right? What about the cosine of x plus y? Can I cancel those? Yeah, again, no. Why not? So we're correct that we cannot cancel either of those things. Because they're not factors, right? 2 is not a factor of the top or the bottom. Just because this term has a 2 doesn't mean the whole top has a factor of 2. Neither is cos of x plus y. So in order to cancel those, we would have to be able to factor them out from both the top and the bottom and then cancel. But since neither of them can be factored from the top nor the bottom, we can't do any cancellation. All right, let's return to the problem at hand then. I'm trying to get the slope of this tangent line. Trying to find the slope of the tangent line to that curve at the point pi comma pi. And in order to find the slope, we said, okay, I need y prime. I need my derivative. Well, now I have y primed. How do I use this to get the slope of my tangent line at that point? well, this y prime, this is dy dx. Yeah, exactly, Tahar. We're going to plug in pi, right? We're going to plug in pi for both x and y. And that's sort of the new thing here, is that in the past, your y prime would only have x's in it, but now it's got both x's and y's. So when we go to plug in to find our slope, we have to plug in the x value and the y value, both of which are pi here. So we're going to take the x and y values at the point of tangency and plug those into this expression. That will give me m tan. There's a notation for this, y prime evaluated at the point pi comma pi. Here's this vertical bar here means evaluated at. So I'm taking the expression for y prime and I'm evaluating it at the point pi comma pi. And this is going to be 2 minus the cos of pi plus pi over the cos of pi plus 2, which is 2 minus the cos of 2 pi over the cos of 2 pi plus 2. Okay, what is the cosine of 2 pi? Good, cosine of 2 pi is 1, right? That is our starting point on the unit circle. It's the far right point. So this is 2 minus 1 over 1 plus 2, which is 1/3. So my line, so our tangent line is y minus y0 equals m times x minus x0. y0 and x0 are both pi. So that's y minus pi equals the slope 1/3 times x minus pi. So this is a pretty standard implicit differentiation problem. You'll have plenty of stuff like this in this week's homework. I wouldn't mind looking at one more kind of where taking the derivative is more the focus, since it never hurts to be certain about what's going on there and why it's going like it is. So let me do a very quick review of why implicit differentiation works the way it does. If we assume that y is equal to f of x, then d dx of something like y to the 5th is d dx of f of x all to the 5th, like this. Which I think we all agree by the chain rule would be 5 times f of x to the 4 times the derivative of f of x, which is f primed of x. This is by the chain rule. Chain and power rule. And now we just plug back in. Well, f of x, that's y. So this is 5y to the 4 times derivative f primed of x would be y primed. So the main thing to remember here is that when you're differentiating implicitly, your dependent variable is treated like a function, right? We treat y not like a variable, but like a function, because y is f of x, right? That was the implicit function theorem. That was the thing we talked about back on Friday, is that along any curve, no matter how weird the expression the curve comes from, if you zoom in and look at one little part of it, you can pretend like y really is a function of x there. You can pretend like that curve is a function, even if it doesn't pass the vertical line test everywhere, so you can't actually write it as a function. If you zoom in on any one part, that one part does pass the vertical line test, so you can assume, at least within a little window, that y is f of x for some function f. And that means when you differentiate y's, you have to treat them like you treat f of x. You don't treat them like you treat x. You treat y's like f of x. And that should be familiar to us from algebra, right? The idea that y is like f of x. Kind of the other thing to pay attention to is what this differential operator says. The variable down here in the bottom, the dx, that tells you what to treat as your variable. So compare this to d dy of y to the fifth. d dy of y to the fifth really is just 5y to the 4. There's no y prime there, because the derivative of y taken with respect to y would just be 1. So it depends a lot on what you're differentiating with respect to, what you're thinking of the variable as. Here, I'm not thinking about x at all. There is no x. The differential operator says differentiate with respect to y. The expression inside only has y's, so there is nothing implicit here. There's nothing implied. But an expression like this, where it says ddx of y to the fifth with different variables, it's implied that y is some function of x, i.e. y is f of x for some function f. So this is why we multiply by y primed at the end of our little differentiation steps. This is why the derivative of x plus y, when taken with respect to x, is 1 plus y primed and not 1 plus 1. Does that make sense? Is this satisfying to everybody? Are there any other questions we want to ask about this? Cool. Yeah, of course. Of course. Happy to do it. It's a little bit confusing at first, but I think it gets more comfy with time. So let's look at one more kind of grindy example where we have to do a lot of differentiation that is somewhat challenging. Not that grindy though. How's about 15 looks like fun. E to the x over y equals x minus y. We can do that, and then we'll talk about the inverse trig stuff. All right. So here I want to find y prime in the expression e to the x over y equals x minus y. Again, here y is implicitly assumed to be a function of x. So every time I differentiate a piece with a y in it, I'll need to slap a y prime on the end. Let's do it. On the left-hand side here, I'll have d dx of e to the x over y. And on the right-hand side, I'll have d dx of x minus y. The object on the right is going to be 1 minus y prime. The object on the left is going to be, I'll write it out kind of schematically, it's going to be e to the x over y times d dx of x over y. That's the regular chain rule, right? If I want to differentiate e to some stuff, I'll always get back e to that stuff times the derivative of that stuff. But now I need to take the derivative of x over y, and I need to do that very carefully. Because there I have an implicit expression all on its own. So this is e raised to the power of x over y times, this is a quotient rule thing. I'll have low d high minus high d low over low low. So that's the bottom times the derivative of the top. And the derivative of the top is 1 minus the top times the derivative of the bottom. Well, the derivative of y is y primed. Right, because I'm taking the derivative with respect to x. And then all of this is over the bottom squared. Does everybody see where that's coming from? And then on the right-hand side, I have 1 minus y prime. Oh, give me just 1 second. Okay, here we go, we're back. So I want to find y prime, which means I need to solve this expression for y prime, which is a little bit challenging. So how would we get started with that? Any advice on how we can get started solving this equation for y primed? Yeah, cross multiplying. Yeah, that's good. That's good. So the denominator over here is 1. The denominator over here is just this y squared. So if I multiply both sides by y squared, then the y squared over here will go away. This e to the x over y is a part of this fraction. You can think of him as being in the numerator. So he's not affected by that. I'll just get e to the x over y times y minus x times y primed equals 1 minus y primed times y squared. And then I can sort of distribute everything on both sides. The long-term goal here is to pull everything with a y prime to the left and leave everything without a y prime on the right, or push it to the right. So on the left, when I distribute, I'll get e to the x over y times y minus e to the x over y times x y primed. And on the right-hand side, when I distribute everything, I'll get y squared minus y squared times y primed. And from here, any term with a y primed, I'll keep on the left. Any term without a y primed, I'll move over to the right. So this guy has to go to the right. This guy can stay on the right. This guy has to come over to the left. That's going to give me is this. So I'll add this over here. So I'll have y squared, y primed. I'm going to leave this here, minus e to the x over y times x y primed equals, I leave y squared on the right, and I subtract this over here. So I'll have minus e to the x over y times y. So we sort of cross multiply and then distribute everything out. And then any term with a y prime goes to the left. Any term without a y prime goes to the right. And we do that so we can factor a y prime out on the left. So when I factor out a y prime here, I'll be left with y squared minus, I'm going to write the x in front, x times e to the x over y times y primed equals, on the left, I'll do the same thing, writing the y piece in front of there, y squared minus y times e to the x over y. And then I can divide over by this piece. So this, which is equivalent to, now we divide over and we get y prime alone. So I'll have y squared minus y e to the x over y divided by y squared minus x times e to the x over y. And there's a startling amount of symmetry here, right? I think that symmetry is kind of beautiful. Everybody's entitled to their own opinion, especially when it comes to what is beauty. But I would say that this is a pretty beautiful expression. Any questions about how we got here? We're definitely at the part of the course where things start to look a little bit like alphabet soup. We got a lot of parts floating around. So organization is important here, right? Try to do just like one thing per line. Make it clear what you're doing in each line. Don't clutter stuff up. Try to write nice and large. Try to put a little bit of blank space in between your lines. You'll be okay. If there aren't any questions on this, I am going to quickly review the derivatives of the inverse trig functions, and then we're going to talk about logarithmic differentiation. Okay, so last Friday we looked up the derivative of the inverse tangent function, and I think we also did the inverse sine function. I'll remind you how this goes. But first, let me just write down the 6 derivatives of the inverse trig functions that you need to know, right? You need to remember these. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. And this pairs nicely with the derivative of the inverse cosine of x, which is negative 1 over the square root of 1 minus x squared. The derivative of the inverse tangent function is 1 over 1 plus x squared. This is probably the most important of all the inverse trig functions and their derivatives. The derivative of the inverse cotangent function is negative 1 over 1 plus x squared. And we begin to see the pattern. The derivative d dx of the inverse secant function, this depends a little bit on who you ask, but I'm going to say that it is 1 over x times the square root of x squared minus 1. And I bet you can guess what the derivative of the inverse cosecant function is, it's the negative of that. Gotta remember these. Gotta remember these, especially these three. Really, especially these two. These two are the most important by far. But you gotta remember all these. And the best way to remember them is to solve problems that involve them. So if you look in the textbook, there's plenty of problems involving these functions. They're not as many as I would like, but here you go, right? You got a few more here and a few more here. So I would strongly advise that you solve problems 49 through 64 in this section of the book until you are real comfy, like real comfy. When I said that the derivative of the inverse secant function kind of depends on who you ask, the difference is precisely what they're showing here. Some people would say that the derivative of the inverse secant function has an absolute value there. Some people would say it doesn't. It depends on the choice you make for the domain restriction of the inverse secant function. Most people go with this definition, which means most people would say there should be an absolute value there. But I'm not going to beat you to death over it. But again, if you want to make sure you have enough practice with the inverse trig derivatives, work problems 49 through 64 in section 3.5 of the textbook. I'm assigning a few of these. I assign a few of these guys, and I think like one or two of these guys, but not a whole bunch. I want to remind you where these come from. So we proved a few of these last Friday. Here's how we get cosine. I think we did sine and tangent last week, so let me go ahead and do cosine for you here. Begin with y equals the inverse cosine of x, which means that the cosine of y is equal to x. I can forgive you at this point if you don't remember a lot about inverse trig functions. I want to direct you, especially if you're feeling at all insecure about inverse trig functions, to the following review material. This. Specifically this. If you don't remember everything from trigonometry about inverse trig functions, please come to this page. Just go to the modules, go to the review material modules. It's like the fifth or sixth link here. Just says trig review. Then click on inverse trig stuff. It's got some really important things that people tend to forget, like this is not a power. It has nothing to do with the reciprocal. It means inverse in the sense of a functional inverse, like how the square root is the inverse of the squaring function. How the natural log is the inverse of e to the x. So if you don't remember how inverse trig functions work, please come here and spend a little bit of time reading this. Make sure that you remember this stuff. All right, so if y is the inverse cos of x, that means cos y is x and 0 is less than or equal to y is less than or equal to pi. We're not going to worry about this part. That's not so important to us. But differentiating, we get d dx of cos y equals d dx of x. D dx of cos y, this requires implicit differentiation. The derivative of cosine is negative sine. So I differentiate the outside, leaving the inside alone. But then since this is d dx, since I'm differentiating with respect to x, I need to multiply by the derivative of the inside, which is y primed, or dy dx. And on the right-hand side, the derivative d dx of x, that's just 1. So I can solve for y primed, and I'll get y primed equals -1 over the sine of y. All right, I'm dividing by negative sine y, so the right-hand side will become negative and the sine y. You can put the negative down here if you want, it just doesn't matter, it's just negative. And now the trick is to rewrite sine of y in terms of x. So at this stage, we'd say, we know that sine y, or sine squared y, sorry, plus cos squared y is equal to 1, which implies, what I have here, sine of y. Sine of y is the square root of 1 minus cos squared of y. And cosine of y is x. So this is the square root of 1 minus x squared. So y prime, -1 over sine y is -1 over the square root of 1 minus x squared, i.e. the derivative d dx of the inverse cosine function is -1 over the square root of 1 minus x squared. Now you really don't want to have to go through this every time you need one of these derivatives. This is an awful lot of work to differentiate a function. So you need to remember the table above. But since this is an honors class, I may ask you guys for parts of this proof or something like that on an exam. I might say, how do I go from here to here? Or something like that. That would be a fair game. The idea is to remember the definition. And here we just use the Pythagorean formula, or Pythagorean identity for sine and cosine. But most important is that you remember these derivatives and you get good at using them. So cooking them up is a good exercise, right? It's a fun exercise in logic and implicit differentiation, and you should be comfy deriving any of these formulas. You should be comfy doing what we just did to get the cosine formula here. But mostly, and especially in your homework, you need to be comfy using these, taking derivatives of functions that involve these things. So I'll hold here for a second in case anybody needs to get this table down nice and clear in their notes. I like organizing it this way. That way the functions and their cofunctions are right next to each other and you can see the relationships. Hold for about 5 more seconds. If you need a screenshot, grab one now. Okay, and now we have this. This was our derivation. I'm not going to do any more. We did sine and inverse sine and inverse tangent last Friday. This is inverse cosine. The other ones, they all go the same way. It's all the same trick. All right, so let's go ahead and solve a problem or two using these. Let's start with g of x. Why not here? G of x is arc cosine of square root x. So since we just did something like that, and we just cooked up the derivative of arc cosine, we might as well. Just to be clear about the notation, arc cosine of the square root of x is the exact same thing as cos inverse of square root x. I grew up using the inverse notation like this rather than the arc notation, so I'm going to use this notation. They mean the same thing. So g primed of x would be the derivative d dx of the inverse cosine of the square root of x. That's my goal, is to just differentiate this function. I know that the derivative of the inverse cosine of x is -1 over the square root of 1 minus x squared. So here I'm going to have -1 over the square root of 1 minus the square root of x squared, because that's what's on the inside of my inverse cosine. And then by the chain rule, I need to multiply by the derivative of the square root of x. Everybody with me so far? Okay. So if you square the square root of x, like we're doing downstairs under the big radical here, you just get x. And then over here, the derivative of root x is 1/2 x to the negative 1/2. This is something that comes from, it's a derivative we've taken a lot so far. So root x, I'm kind of being fast there, but I'll say root x primed is x to the 1/2 primed is 1/2 x to the negative 1/2, which is 1 over 2 square roots of x, like this. So in the end of the day here, I'll have -1 over the square root of 1 minus x times 1 over 2 square roots of x, like that. Any questions on this one? Okay, we can combine the implicit differentiation stuff with the inverse trig stuff. I don't think your book actually has anything like that, which is sad. Yeah, no, it doesn't, does it? Not one goddamn piece. That's tragic. So nothing anywhere in here? No. All right, they just want to move on to application problems. That's okay. So the next thing I want to talk about is logarithmic differentiation. I trust that you guys are now ready to handle all of the 3.5 homework. It's not that bad. There's plenty of things in there that ask you to take big, scary looking derivatives, and it'll take some time, but you just have to be careful and apply the rules. So the next section, 3.6, is on log derivatives. We've already proven that the derivative d dx of the natural log of x is 1 over x. All right, we're not going to go through that again, but this is your first rule that you need for this section. It is, of course, important. And then by the change of base formula, we can write any other base logarithm in terms of the natural log as like if I have the base b logarithm of x. Does anybody remember the change of base formula? If I want to change that to a base c logarithm, that would be the base c log of x over the base c log of b. But I want to change it into a natural log. So this is the natural log of x over the natural log of b. The top is a function of x. But the bottom here is a constant. So it can be useful to think of this as 1 over the natural log of b as a constant multiple times the natural log of x. If b is just a constant, then the natural log of b is just a constant. The natural log doesn't magically turn this into a variable, right? Just like how if you know c is a constant, then c squared is a constant. Nothing special there. What this means is that if I want to take the derivative of some other base logarithm, the derivative of the base b logarithm is equal to the derivative of 1 over the natural log of b times the natural log of x. And since 1 over log b is a constant, it just pops out. And we already know how to differentiate the natural log of x. That's 1 over x. So the derivative of some other base logarithm of x is 1 over x times the natural log of the base. That's all. Nothing too special. So d dx of the base b logarithm of x is 1 over x times the natural log of b. This is not a super big deal because we in general don't fuck around with logarithms besides the natural log. But as a, we're building up, we're in the section on derivatives of logs, so it makes sense to talk about how you get the derivatives of other logarithms here. This is not the good stuff. The good stuff from this section is how you can use logarithm properties together with the chain rule to get some really nice derivatives of functions that are otherwise very, very, very hard to differentiate. Okay. Any questions so far? Okay. Let's see, we started at like 11:15, right? We were a little bit late today. So I'm gonna go just a little bit further. I'll let you guys go in just a second here, but I want to show you what logarithmic differentiation is, why this is so useful. The thing that makes this useful are the algebra properties of logarithms. I'm going to use the natural log here, but yeah, the natural log of a times b is the natural log of a plus the natural log of b. The natural log of a to the n is n times the natural log of a. And the natural log of a over b is the natural log of a minus the natural log of b. These three properties together with the chain rule. I'm not sure, sweetie, they should. Oh, wait, I might have them. You also? So these three properties together with the chain rule are really useful in differentiating big expressions. Imagine I want the derivative y primed of y equals x minus 3 to the 20 times x plus 1 to the 3 halves all over the square root of x times x plus 4. I'll prepare your butthole, right? This looks really unpleasant. You know, this is a lot of quotient rule and chain rule, right? The outermost thing that's going on here is the quotient rule. And then when you want to differentiate the top, that would be a product rule. But within that product rule, you've got a big power rule and a big chain rule. It's hellacious. Directly, this requires the quotient rule, the product rule, the chain rule, and the power rule. It sucks, right? This is a horrible thing to differentiate. This is where logarithms are going to save the day. I'm going to use these properties up here together with implicit differentiation to get the derivative y primed much easier. Instead of jumping in directly, take ln of both sides. I'll get the ln of y equals the ln of all this shit. X minus 3 to the 20, x plus 1 to the 3 halves over the square root of x times x plus 4. I will now use the algebra properties of logarithms. Oh, they can fed baby. Oh, yeah. All right. I'll now use the algebra properties of logarithms to expand this thing out as much as I can. After I've expanded it out, I'll be able to differentiate each piece on its own. So here's what we're going to get. First, I use the rule that says log of a fraction is the log of the top minus the log of the bottom. So this is the natural log of x minus 3 to the 20 times x plus 1 to the 3 halves minus the natural log of the square root of x times x plus 4. And then I can expand these pieces. As ln x minus 3 to the 20 plus ln x plus 1 to the 3 halves minus ln of x times x plus 4 to the 1 half. And now I can bring each of these powers down. That's one of my other rules for logarithms. So the logarithm of a power, a to the n, is n times the logarithm of a. So this first piece is, 20 times the natural log of x minus 3. Plus the second piece is 3 halves times the natural log of x plus 1. Minus this third piece is 1 half natural log of x times x plus 4. This guy, I still have to expand a little bit more. So let's do that. This is 20 times the natural log of x minus 3 plus 3 halves, times the natural log of x plus 1. This is going to be minus 1/2 natural log x minus 1/2 natural log x plus 4. All right, so this is like one of those pre-calculus problems that says expand the logarithm as much as possible. There it is, expand it as much as possible. Why is this good news? Well, because each of these pieces, right, this process is easy. We teach kids how to do this in college algebra. And now each of these things is really easy to differentiate. It's just going to be the log derivative together with the chain rule. It's very, very simple. So what I'm going to do now is apply d dx to both sides. You do have to be careful here because the left-hand side is not y, it's ln y. So when I apply d dx to both sides, the left-hand side will be d dx of ln y, and the right-hand side will be d dx of all this. So now 20, I keep wanting to write that as a 3. 20 times the natural log of x minus 3 plus 3 halves times the natural log of x plus 1 minus 1/2 times the natural log of x minus 1/2 times the natural log of x plus 4. All right. Now we need to pay attention as we differentiate on the left. It's an implicit differentiation thing, right? I'm differentiating implicitly because there's a y inside, but I know y is a function of x. The derivative of ln x is 1 over x. So d dx of ln y is 1 over y times y prime. And on the right-hand side, I use the chain rule. This 20 is a constant multiple. The derivative of the natural log of x minus 3 is 1 over x minus 3 times the derivative of x minus 3. So I'll just write each of those as the prime. And then I have plus 3 halves times the derivative of ln x plus 1 is 1 over x plus 1 times the derivative of x plus 1. Again, just using the chain rule. Minus 1/2 times the derivative of ln x, that's just 1 over x, no chain rule there. Minus 1/2, the derivative of ln x plus 4 is 1 over x plus 4 times the derivative of x plus 4. So here's all my little chain rule stuff. And I think, if I'm not mistaken, yeah, this, and this are all 1. So the left-hand side, I have 1 over y times y primed equals, on the right-hand side here, 20 times 1 over x minus 3 times 1. This is just 20 over x minus 3. So this little piece here is 1. This little piece here is also 1, and this little piece here is also 1. From the chain rule there, don't give me anything interesting. Then I'll have plus 3 halves times 1 over x plus 1. That's 3 over 2 times x plus 1, like this. Then I'll have minus 1 over 2x, and then minus 1 over 2 times x plus 4, like this. And I think you would agree that the differentiation step here was not hard. All right, differentiating 20 ln x minus 3. The 20 is a constant, comes along. Derivative of ln x minus 3 is 1 over x minus 3 times the derivative of x minus 3. And it's just pieces like this for each of the terms. The final move here is to multiply it back over by y. So y prime is 20 over x minus 3 plus 3 over 2 times x plus 1 minus 1 over 2x minus 1 over 2 times x plus 4 all times y. And then if you really want to, you can plug back in for y. It depends on what the problem is requiring. Y prime is 20 over x minus 3 plus 3 over 2 times x plus 1 minus 1 over 2x minus 1 over 2 x plus 4. And then what was y? Y was this thing. So that's x minus 3 to the 20, x plus 1 to the 3 halves, all over the square root of x times x plus 4. I know what I would rather do. If I had a choice between using this or jumping in with the massive combination of quotient rule, product rule, and chain rule that you need to differentiate this directly, I would way rather do this. This is called logarithmic differentiation. This procedure is called logarithmic differentiation. And logarithmic differentiation is important in a lot of ways. The first reason it's important is what we've just outlined, that it lets you differentiate more easily and more confidently some really big, nasty expressions, like big fractions with lots and lots of pieces multiplied. Logarithmic differentiation is your friend. There's also shit that you can only differentiate logarithmically. I'll talk about that next time. So this is where I'll make a note. This is where we're going to leave off for today. And next time I will pick up talking more about logarithmic differentiation. And we will move on from there. So I think Wednesday, we didn't get to any related rate stuff today. That's fine. Wednesday, we will talk a little bit more about logarithmic differentiation and related rates. And then on Friday, we are going to have our next student teaching. It's Chris and Kevin. I forget, I'm sorry. I'm so sorry, guys. We went through our rehearsals last week, but section 3.10 will be student taught on Friday by the individuals doing student teaching for that section. So sorry, guys. Is it Chris and Julio? Yeah, Chris and Julio. Okay, thank you guys. So sorry. So yes, that's the game. This Friday, Chris and Julio will do section 3.10. And then I think probably next Monday, Kevin is going to do section 4.1. And that's where we're going. So Wednesday will be lots of work with related rates, a little bit more logarithmic differentiation, but lots of work with related rates. And then Friday will be linear approximation and differentials. And the following Monday will be min and max value problems. I'm still working on your homework for this week. I think I might have published it already, but I'm gonna add a couple problems to it. I don't think I'll be removing anything, so you're good to go ahead and get started on that. It's gonna be due next Monday, of course, at the start of class, but watch out. If you finish it, just be aware that I'm gonna add a few more problems. It doesn't have any linear approximation problems yet, so I'll throw a few more of those in. But that's it, guys. I will see you all on Wednesday when we will talk about related rates. And yeah, of course, Katie, if you guys want to talk about projects, Kevin and Katie, of course. Oh, I see. Okay. Come by office hours or send me an email. The page reference in the syllabus might be wrong, but that thing is in there somewhere. It might also depend on the version of the textbook you have. So let me know what version you have. Come by an office hour. We'll talk about it there, okay? Or send me an email. Either one's fine. All right. Take care, guys. And I will see you next time or in office hours.